Hello, we're Group 7 and we'll be presenting our project on the dual monitoring of ECG and EEG to identify causes of syncope, or as we call it, MEECS. Firstly, we'll be discussing our need and approach. Syncope, a common clinical problem, is a sudden, transient loss of consciousness that can be caused by seizures, sleep disturbances, dehydration, among many other afflictions. Taking a look at some numbers, syncope patients account for 1 to 3% of all emergency department visits, and hospitals are spending around $2.4 billion per year to treat them. We learned from clinicians that diagnosing causes of syncope can be challenging and costly for two main reasons. First, while syncope can be an indicator of serious underlying cardiac or neurological illness, it can also manifest in many other illnesses, making it difficult to pinpoint a root issue based on a medical record and initial examination alone. In fact, only 50% of first visits produce a diagnosis, and 35% of these syncope cases are deemed serious enough for readmission. Second, the current standard of care, which involves patients receiving periodic electrocardiogram and electroencephalogram screenings, is suboptimal. An expensive hospital readmission can last for 3 to 5 days, when most of the time is just being spent setting up electrodes and waiting for ECG and EEG readings, or until another syncopal event. To make the screening process more efficient, cost-effective, and comfortable for patients, we sought to design a wearable dual ECG and EEG monitor for hospitals to lend out in the common event that a patient's initial evaluation is ambiguous. Our vision was for syncope patients to be able to screen at home, cutting down on hospital stay expenses while allowing their head and heart data to be sent directly to their physician. So we approached this project with several design goals. Among those we were able to accomplish were making our device accurate and reliable, capable of wireless transmission, and cost-effective relative to the standard. We evaluated these goals by using simulated syncopal datasets to test our software's ability to flag events and measuring error, observing the time it took to complete data transmissions, and creating cost estimates from our bill of materials and comparing them to existing costs. Unfortunately, we were not able to execute some of our other goals, including usability surveys and interface readability surveys, given our distance from campus. Most of the design specifications that we presented on in December have remained unchanged, since we were able to validate with our clinical mentor that the signals we were receiving were acceptable. In that sense, we didn't have to change the frequency range or sampling rates that we'd used previously. The main change was the physical size of the backpack that we used to house all of our electronics, which will be discussed later. Now I'm handing it off to Evan.
Thank you, Jelly. Now let's take a look at our design process, starting with our EEG component. The EEG component of our project takes brainwave data recorded by electrodes and is able to transfer that data to a physician's computer in a form that can be viewed. Let's take a look at how it works. Electrodes on the forehead made out of a PDMS material record EEG signals. That data is then sent to the OpenBCI circuit board. Then, using Bluetooth technology and Python code, that data is wirelessly streamed in real time to the Raspberry Pi worn by the patient. Once on the Pi, the EEG data is converted to a comma-separated value file and then sent over the internet via an email to the physician's computer so that it can be viewed using our Python GUI. Here is a photo of the EEG headband developed by the Platt Lab and used in our product. In the background you can see the PDMS electrodes, and in the foreground the OpenBCI circuit board.
Our miniature electrocardiograph is lightweight and able to generate high enough quality data for analysis of the causation of syncope, according to one of our cardiologist mentors. The signal is first captured by an integrated circuit provided by SparkFun, to which 3 electrodes are attached. The integrated circuit performs some basic baseline filtering and outputs an analog signal to the Arduino. The Arduino serves as an analog to digital converter and also provides an extra layer of electrical insulation. The Raspberry Pi integrates the ECG data and stores it along with the EEG data. The Pi also processes the data in order to flag syncopal events. Here is a more detailed view of the circuitry. We sought to create a simple, clean setup as this would lower the risk of the device malfunctioning. The setup does not require many wires, thanks to the serial interface capabilities of the Arduino and Pi. In the top right is a photo of the three main components all connected. In the bottom right is a sample ECG signal, in which one can clearly see the QRS complex, a small P wave, and a T wave. We sought to design a housing for the electronics that would be comfortable for the user to wear for 24 hours. This began with a box for the electronics, which is fairly thin at a height of 6 centimeters. The components are held securely in the box so they do not move around, and there's also venting to keep the components cool. The box will be made out of a high-performance, high-temperature plastic, such as PEEK. The box slides into a backpack, which is zipped closed and features cushioning on both sides so the user may lay back comfortably. The straps are adjustable
to fit users of all heights. The electrodes come out of a secure opening to be attached to the patient. This backpack was sewn together out of waterproof fabric using the BioMakerspace.
Thank you, Seth. I will now talk about our major results. We have created a Python application that displays EEG and ECG data in order to show our results. When you open the GUI, you are greeted with the screen that you see here. You can click the Visualize EEG or Visualize ECG Data button. After clicking either of those buttons, a file explorer like the one you see here will pop up. Next, select the file that you would like to look at. After clicking Open, a plot like the one you see here will show up. This plot actually shows Seth's EEG data that we were able to collect with our device. If you click the Help button in the bottom left corner of this plot, this Help menu will show up, which gives you a bunch of useful functions that you can use to interact with the data. We were also able to do some data analysis and validation in order to identify syncopal events in simulated EEG data. In order to simulate a syncopal event, as shown in this plot in blue, we took Seth's actual data that was collected using our headband, and then times it by a scaling factor between 20 and 40 seconds in order to simulate syncope. We then computed the line length feature over the entire dataset using a moving window, and then implemented our syncopal event flagging algorithm, which takes the inverse of the line length feature and sees when it crosses a certain threshold and places a flag. It then waits to place the next flag for a certain amount of time, and this makes sense because we see that the line length feature decreases drastically during syncope, and also when someone faints one time, you have to wait a certain amount of time before they can faint again because they have to come out of the original fainting spell. This had a mean average flagging error of 2.4249 seconds. We also did some machine learning on our data, using the k-means clustering unsupervised learning algorithm to separate syncopal and non-syncopal points in our line length feature. We see from the plot that this was highly successful. While it is important to keep in mind that this was a training dataset and a simulated one, we are excited to see this result, and we think that because the k-means clustering algorithm was able to find a decision boundary, this algorithm will generalize well to test data in real patients.
The total cost of our product is $536.54, which meets the goal of creating a low-cost medical device for syncope. We've broken up this total cost into 4 sections, each representing a major part of the entire product. The first is the ECG, and those 5 items listed below account for $62.80. Next is the EEG, the bulk of the cost. In total, $347.83, which is made up of the 4 components listed below. Next is the backpack, and those 4 items, either making up the composition of the backpack or the casing for the electronics, account for $43.96. Last is the Pi, and the battery pack for it, which accounts for $81.95. We were fortunate to receive some of these items free of charge from the generosity of the Stevenson Foundation Educational Laboratory as well as the Platt Lab, and those items are marked with an asterisk. Now, the price of those is included in the total cost. Our future plans are as follows. We intend to use Amazon Web Services in conjunction with our own software infrastructure to collect and automate the EEG processing with one button press. We are pleased with our progress on the flagging algorithm, and we plan on improving it to correct for the 2.4-second error. We intend to conduct usability tests and comfort tests to gather data on any suggestions for ergonomic improvements. Finally, we hope to work with Dr. Weiss and the Penn Presbyterian Medical Center Heart and Vascular Center to test on patients. Last, thank you to everyone who has helped us along the way. Our successes are a direct result of your assistance and mentorship.